No more questions. Going once. Going twice. 3 times a day. Alright. But I don't think I have a few that I think are pretty tough, and we'll see how you feel about them. So some of the ones that stuck out were the ones involving x, like 37 to 41 and 43 to 47. Those ones are a little different. So I wanted to kind of showcase how those fit together and how you can solve them. Let's start with 37. So it says in 37 we have the following problem. We have tangent of sine inverse of x minus 1. So this is what we called on Thursday a composite function, meaning it's two functions in one. We recommended the steps for doing these kinds of problems were to draw a triangle that represents the first part of the problem, and then use that triangle to solve the second part, most often with Pythagorean's theorem. So that's what I'm going to attempt to do. I'm going to take this inner piece, the sine inverse of x minus 1. I'm going to attempt to use it to try to draw some kind of triangle. And with that triangle, I'm going to attempt to find the tangent of that triangle. Here we go. Let's start with, I draw a triangle. Ooh, so beautiful. Now you can take the information that is in this triangle and put it into, that is in this column and put it into the triangle. That is the x minus 1. There's only one issue. Right now we have x minus 1 for my sine function. This is supposed to somehow be equal to opposite over hypotenuse. Because remember, sine is always opposite over hypotenuse. I don't have a fraction. That's a problem. So what I'm going to do is rewrite this in fraction form so I can find the opposite and the hypotenuse. The modification I'm going to make is take this x minus 1 and put it over 1. This is always allowed in mathematics. You may always take any function or value and put it over 1 to turn it into a fraction. This means I now have a possible opposite, x minus 1, and a possible hypotenuse of 1. I'm going to now put those two pieces in my picture. I start by declaring my angle, theta, right there. I put the opposite, x minus 1, and my hypotenuse, 1. So far so good. Next, and then use Pythagorean's theorem. Pythagorean's theorem will tell me what that missing side is. Again, if I want to do the tangent, I need the opposite and the adjacent, which I have the opposite already as x minus 1. I would now need the adjacent side as well. So I'm going to use Pythagorean's theorem on this very weird equation. Let's do it. My opposite is x minus 1, so opposite squared plus the adjacent squared equals the hypotenuse squared. Even though it's weird values like x minus 1 and 1, I'm still using Pythagorean's theorem the same as I normally would. Now, my goal is to get a by itself, so I would subtract this x minus 1 squared over, so I get 1 squared, which is 1, minus x minus 1 squared equals a squared. Remember, I'm always allowed to add or subtract from both sides, as long as I do it to both sides. And I will square root to get x by itself. So we end up with a is equal to the square root of 1 minus x minus 1 squared. This is my missing side a. Which means my picture up here, I go back to that picture, I do the square root of 1 minus x minus 1 squared. And now I can talk about the tangent function. Remember, the tangent requires us to have the opposite and the adjacent. I now have those two pieces. I'm going to take those two pieces and plug them in and answer my problem. This thing is equal to the opposite side, x minus 1, over the adjacent side, square root of 1 minus x minus 1 squared. Now in the text, I believe they have written the simplified version of that. And by simplified, I mean nasty. I think this is much nicer than the book version. The book version is simplified in that they took x minus 1 and actually squared it out using FOIL, and then simplified the bottom, and they fixed the radical denominator. But this is perfect. It's exactly what we're looking for. It is the opposite side divided by the adjacent side, which is the tangent function. This is how you may have to approach some of the other problems in this section. Again, we use the inner piece to set up the triangle in whatever way we can. In this case, I had to force it to work by creating a fraction so I could use the sine inverse function. Once I had those pieces, the same as if they were numbers. I find the missing side, using Pythagorean theorem, and then find the actual trig function itself. Again, the textbook's answer looks different. It has the same value. Sure, 53. So the Google applications. All right, questions on 37. 37, 39, 41, they're all really similar. They have a variable in them instead. There is an example like it. I used to try to share the entire chapter, the entire section. There is an example right before the homework assignment that is going through how to do this exact same problem, or one very similar to it. So if you need the same example, look back one page in the homework and it will be there. 53? Sweet. Let's see how good my handwriting is today. Terrible like always. Nice. Alright. Suppose a 13-foot ladder is leaning against a building reaching to the bottom of a second floor window 12 feet above the ground. Okay. What angle in radians does the ladder make with the building? The big thing on 53 and onwards is being able to take the information you described, put it into a picture, and then apply geometry skills. Let's try that with this problem. In this case, I'm going to start by drawing a picture. Let's start with the building. Ooh. There's a house. It's got a door. It's got some windows. Cool. It's a 3-story house, apparently. All right. We have, according to this thing, a 13-foot ladder leaning against a building to a window on the second story. So I'm going to put my window right there. 13-foot ladder, 12 feet up. The trickiest part of many of these kinds of problems is to be able to take the information you've been given in the problem and reliably turn it into a picture. Most of this stuff, useless. What I care about most, 13-foot ladder, 12 feet off the ground. That's the important components. And the last one is very particular. This is where the most trouble will give you if you didn't read the problem correctly. It says, what is the angle in radians between the ladder and the building? That means theta is right here. Between the ladder, the diagonal line, and the building, up there. That has to be where theta is. If you want to solve this problem, the best way is to look at the pieces I have and use an inverse function. Well, if this is theta, that makes this side the adjacent side of the theta, and that side the hypotenuse to theta. So I'm going to use cosine. So I apply cosine. Since I want to find the angle, I use cosine inverse. I plug in 12 for the adjacent and 13 for the hypotenuse. And I make sure my calculator is in radians. I cannot do that without a calculator, so I'll pull mine out. Ooh. Calculator. Double check it's in radians. It is. Lucky me. Cosine inverse, 12 over 13. I got a radian answer of 0.3948. And the problem says, it doesn't specify how many decimals, so I go to 4. Again, the tricky part about this problem is being able to reliably produce the picture that allows me to actually solve it. If I put those numbers in the wrong spot or read the angle wrong, there's a chance I still somehow wind up with the right answer. Like, you would be surprised. There's also a chance you get the completely wrong answer. In trig, that's what's neat, because there's only so many components you could possibly have, right? If you use the wrong trig function, you're going to find that angle. But if you put the numbers in the wrong spot, it might end up working out somehow. Because math is weird that way sometimes. This is how you do it. Yes. Okay, it's 55. This one pulls something from geometry that you can need to remember. So let's pull out 55. Oh, I'm sorry, I didn't answer the questions. Were there any questions on 53? Luis like, no, I got this, man. I'm too good. All right. 55. 55 does, in fact, talk about an isosceles triangle. Can you describe the problem for me there, Ebony? So theta down here. Okay. So, thank you, Ebony. You are correct in your description of the problem. I have decided to turn that description into this picture. So I have two congruent sides of 9 inches, and the third side it registers 8 inches, you said. And I wanted to know about theta being down here between the 9 and 8 inch sides. You could ask, well, what if I did it on the left-hand side? You get the same answer. Remember, that's one of the properties of geometry. Okay, so how do we find that missing angle?
Just put a line down the middle and cut the 8 and 4.
It does two parts to that. It will cut the 8 into 4 and 4. That part is very important, but it does one more thing, which you also mentioned.
We make a right triangle.
Yes, remember to use the trig. We need a right angle. So now I'm going to focus on just one of these pieces. This piece. We have a 9 here. We have theta down there. We have 4 down here. And I want to now find that missing side. Or sorry, my missing angle. Perfect suggestion there, Scott. This is the kind of one in geometry. It's that in order to do the trig functions, we need a right triangle. So if they'll give us one, we have to somehow make one.
So would we use cosine?
I would use cosine again. Yeah, 55 uses cosine as well. So I do cosine inverse. I would do the adjacent side, which is 4, over the hypotenuse, which is 9, and get a solution. Now I'll make sure to read. 55 says it does not specify whether it's doing degrees or radians. My calculator is already in radians from the previous problem. I'll probably just keep it in radians. 1.1102. Looks weird, but that's right. Did anybody get it in degrees by chance? Okay. Let's see, in degrees, that'd be what, 64 degrees? Somewhere in there? So like I was telling you guys in class, when it comes to degrees, I usually try to round to the nearest degree. When it comes to radians, I try to get 4 decimals. Unless it specifies otherwise.
63.6.
It wasn't too bad.
How do you know all this stuff?
A good approximation. Multiply your number by 60.
Wow.
Because the normal multiplication is 180 over pi, but pi is roughly 3. So 180 over 3 would be 60. So it's a quick little conversion. It's not always great, but it's good if you have to make yourself look good. Like math teacher up here at the front. Must look good. So far, great suggestions on problems. Loving the real world applications. Other ones that were freaking you guys out? Any looked bad?
Can we just do like, I don't know, 25, just so I know I'm doing it right?
Yeah, sure. So these ones involve the unit circle, so I'm actually going to do this. I will show you my mental process using the unit circle only. Ready? All right, 25. So, someday I will show you guys whenever I do the homework. I draw a unit circle every time. It's in the top right corner of my problems. When I know I'm going to use it, I draw it. I don't have to think about it or remember it. It's really nice. So for this problem, number 25, I'm going to draw a rough unit circle very quickly here. And I started off always backwards.
What the fudge?
With just those pieces, I'll answer all my parts. So notice I don't draw the full unit circle because I remember my properties of how they flip around. So I can find them all. It's really nice and simple. Let's go ahead and answer number 45. Number 45 says, we're supposed to find tangent inverse of sine of pi. Checked? Yes. So first thing, I do the inside piece first. So I do sine of pi. So sine, remember, is the y value. So I go to my unit circle, y value. So this says let's do tangent inverse of 0. So far, okay? Once I've got that piece, I then have to ask, okay, where is tangent going to be 0? Well, there is a third part of the unit circle. So remember, the first value tends to cosine, second value the sine. There's a third part that deals with the tangent only. That happens in two places. It happens at 0 degrees and at pi degrees. Again, I have those memorized. So finding those values is not too hard. Remember, you can always use, to find the tangent value, you can always test the sine value divided by the cosine value, but that can take a lot of time if you're not careful. With some of those ones in that section, you may have to use coterminals, like -5/2. You cannot do a unit circle, but you could coterminal it to find one that is in a unit circle. So you notice the problem say, if possible. I think there's one. There's two that are not possible with unit circle, but they are possible with something else. Using the technique we used like on the previous one, 55. Want to do another one with that?
Sure.
Okay. Pick one.
I don't know. 27.
27?
Yeah.
Alright. What 27 say, Scott?
Inverse of tangent, and then sine pi over 3. Okay.
Good. Okay, so again, I do the inside piece first. I do sine of pi over 3. So sine of pi over 3, I go to my unit circle. Sine of pi over 3 would be square root 3/2. This becomes tangent inverse of square root 3/2. That is not possible without a calculator. The reason being, there are no tangent values on the unit circle of square root 3/2. Now there are two that are square root 3/3, two that are square root 3/1, but none that are square root 3/2. So this one you say, not possible. Now a calculator will tell it to you right away. But this question asks to do it without a calculator, not possible. That's a perfect example. Good choice. Again, the values for sine and cosine are 0, 1/2, square root 2, 2, square root 3/2. The values for tangent are 0, square root 3/3, 1, square root of 3, and undefined. Those are values that you can memorize if you wish. I strongly encourage it. Because without it, these can be pretty tough. Any other ones? Okay. So, stand up here for a while. Be all awkward. Have a good weekend, too. I'm sorry. Thank you. Don't forget, you may also try to do class. You don't have it finished during class. So on 37, I need you.
Mr. Dodson, you're needed in the office. Mr. Dodson, you're needed in the office.
So, we have the following problem. We have tangent of sine inverse of x minus 1. So we talked in class about these composite functions and how to do them. The main steps that go into them is typically as follows. If the inverse is on the outside, we're probably going to use unit circles or a calculator. And on the inside, like most of these are, you're going to end up setting up a triangle and Pythagorean's theorem as part of your steps. Now, this one's weird, and the ones after, like 39 and 41, are weird because it has x in it. Now, because it has x inside of this function, there's a change we have to do to get this to actually turn into the triangle map we're expecting. My goal, as you'll recall, for these inverse composite problems is to somehow make a triangle. Now, I can only do that if I have it set up as a ratio, a fraction. Because sine inverse, as we'll recall, inside of sine inverse is supposed to be opposite over hypotenuse. So I want a fraction, I want a ratio. I don't have that. I have x minus 1. So let's make a change. Remember, algebraically speaking, you're always allowed to make modifications to your problem as long as you follow good algebraic principles. So that's what I'm going to do. I'm going to modify this problem a little bit to get it to interact correctly with the kind of problem it's supposed to be. I want to create a fraction inside of this problem. Here's what I'm going to do. I take this function and rewrite it as tangent of sine inverse of x minus 1 over 1. I'm always allowed mathematically to put something over 1. And I can put a single number over 1, like 6 over 1 is 6, 5 over 1 is 5. X minus 1 over 1 is still x minus 1. I haven't changed the problem yet. But this is necessary because I cannot turn this into opposite over hypotenuse unless it's a fraction. So I have to make this first clean step. Once I've done that, now I go back to the problems where we had before, where I'm trying to create a triangle. Now these triangles will have weird sides because my sides have a variable in them. But it does not change the rules. I'm still going to set up a triangle. I'm still going to use Pythagorean's theorem. I'm still going to find the inverse function. It's just now it has x. There we go. Step 2. I take this problem, turn it into a triangle problem. Well, I got a right angle down there. I have theta down here in the corner. And I have sine inverse to find. Sine inverse, as it says in the problem, is x minus 1 over 1. That means my opposite side to theta, which is over here, is going to be x minus 1. My hypotenuse to theta is going to be 1. That's looking pretty decent. What do I have this in? Oh yeah, it's in. If I want to do tangent, which is the goal of this problem, is to do the tangent version of this problem, I need this adjacent side, which I do not currently have. So I need to make it my next step is to find the missing side using Pythagorean's theorem. Remember, for right triangles, you may always find the missing side using Pythagorean's theorem or other trig steps. I want to do Pythagorean's theorem, which means I need to do Pythagorean's theorem with 1 and x minus 1 as 2 of my sides. It's going to look a little funky, but notice that it's the same properties and principles we've been talking about. Here we go. Opposite, x minus 1, squared, plus the adjacent, which I'm going to call a squared, equals the hypotenuse, which is 1 squared. So Pythagorean's theorem. The opposite squared plus the adjacent squared equals the hypotenuse squared. A squared plus b squared equals c squared. Now you'll notice that when I do this problem, my goal is to get the a, the missing side, by itself. I'm going to do that algebraically. Getting a by itself involves moving everything else over and then taking a square root. Now your book simplifies a lot more than I do. So the book's answer will look a little different than mine. That's okay. They are still the same solution. In the book, they tend to simplify a lot more using algebra. So example, they would FOIL this out. I did not. I saw no reason to. X minus 1 squared is the side of a triangle. It's a number. So I move it over by subtraction. A squared equals 1 squared is obviously 1. I can simplify that pretty easily. Minus x minus 1 squared. I move that side over. I want to get a by itself. It's currently a squared, so I take a square root. This means I get a, my missing side, is equal to the square root of 1 minus x minus 1 squared. It looks weird, but it's following all the same principles I've been doing the entire time. I used to set up a triangle, use Pythagorean theorem on that triangle. I've now found the missing side. The missing side is this weird fraction, 1 minus x minus 1 squared. Now the question asks specifically about tangent. So now I go back to this picture and I say, okay, what is the tangent function? Tangent is opposite over adjacent. Take the opposite side, x minus 1, over the adjacent side, which is this nasty square root, 1 minus x minus 1 squared. That's the answer that I got and is correct. The book's version is a little different, and it's also correct. What the book did, again, was they FOILed this thing out. They took x minus 1 and squared it, simplified as much as they could, and I believe the book also moved the radical to the top. Again, those seemed like extra algebra steps to me. The goal of this problem was to do the trig right, and the trig is right here. The rest of that is just algebra stuff. I'm going to stop right there. The book solution. And for future reference, if you ever want to know if your solution and the book solution are correct, they look different, but you think you did it right, graph them. Right? In a graph, it'll show you if they are the exact same picture, then it should be the same answer, even if they look different. That's a common trick that I use a lot if I'm not wanting to simplify a bunch of stuff. So, on this one, this was number 37. The book's answer, yeah, their answer, they simplified the bottom by foiling it out. X minus 1 on top. They did 1 minus x minus 1 squared is x squared minus 2x plus 1. So they folded it out, and they simplified the 1 and distributed the negative. So the book answer was 2x minus x squared, which is the same exact solution, just simplified. And notice they didn't even bother bringing the radical to the top. Like, once you get farther in math, you start looking at some of those problems and going, that's the 9th grader's problem. That's the 10th grader's problem. Let them do that problem. We're stopping here because we did all the hard work. In college, we call that's the undergrad's problem. We're the grad student now. We don't need to do that lazy work. Somebody else will do it for us. There it is. I can do another one. I can do number 39 in the same basic way. Is you force it to be in fraction form, so you can create a triangle. Then you use Pythagorean theorem with those sides, and then set it to find the correct trig function. It is not difficult. It is weird because we're not using number values anymore. We're using equations. This is pretty common. If you want to know its application, physics. A lot of physics has variable mathematics, where you have to move numbers around without knowing what they are. To be able to isolate a variable by moving the numbers, great skill if you want to go into that field. Got about 2 minutes until we go to lunch. Other questions? Okay. I'll work through a few more when we get back to lunch. If you guys don't have any suggestions, I'll work through some that I think are fun. Otherwise, do not forget to do tonight. If you don't get it done in class, you're welcome to turn it in a Google Classroom. Somebody asked whenever we were coming in this morning, this is the last part of this chapter. The quizzes from last time will be graded and put in tonight. There's one person going to take theirs yet. They'll take theirs tomorrow, and then you'll get your quiz back after that. We review the chapter tomorrow. Remember, this test will be split into 2 parts. It will be split into part where you are allowed to use a calculator and encouraged to use one, and part where you are not. There'll be some of the questions from our quiz last week will be in the not category. No calculator, no notes. There'll be questions about graphing. Those in the not category. You guys do it without a graphing calculator, without a calculator of any kind. And then there'll be ones that are, please, use the calculator. Use all of it. Every piece you can. Most of that will be from this section. I'll pause and we'll continue when we get back to lunch. Alright.
I can't tell if you're
41.
Jimmy or Sunbird.
Oh, this is a fun one. Okay. 41 has two big ways you can approach it. Kind of depends on how you want to see it through. I'll show one way. At the end, I'll show another. 41. So, I could do 41 the same way we did 37, where I set up a triangle, force the fraction to exist, and then just apply the components. Or, I could try to make the fraction work a slightly different way, which we're going to start with. So, 41, we have tangent of sine inverse of x plus 1/2. So, step one, is like before, I want to force a ratio in here. Remember, if I have sine inverse, I opposite over hypotenuse between the nearest fraction. And to do that, I already have a fraction here, 1/2. I'm going to use that to guide me to get to a full fraction. But to do that, I need to have my x also be over 2. So my first step is, I'm going to rewrite this equation. But instead of x, I'm going to put 2x over 2. Remember, those two are the same thing. If I cancel 2s, I'm left with just x by itself. Those are the same. This allows me to turn these two and combine them together into one fraction, a little easier than what I would have normally. This becomes tangent of sine inverse of 2x plus 1 over 2. This is one way to do it. I could also just put the entire thing over 1, but that makes it really look nasty. You know, with a fraction inside a fraction, it gets bad real fast. I like this version better. Now, I did the same thing I did before. I create a triangle, assign my sides using sine, and then Pythagorean theorem solves the rest. There's my triangle. It's sine inverse, so there's theta. My opposite side is 2x plus 1. My hypotenuse is 2. And now I use Pythagorean's theorem. Pythagorean's theorem states a squared, 2x plus 1 squared plus b squared equals c squared. So I set up my Pythagorean theorem problem. And as like before, I solve for the missing side. Subtract the 2x plus 1 squared over. I get b squared equals 2 squared, which is 4, minus 2x plus 1 squared. Then I square root both sides to get b by itself. Again, following some basic algebraic rules here. B is equal to the square root of 4 minus 2x plus 1 squared. Again, the textbook will simplify this down. I'll leave it right there because I'm lazy. So here's my missing side. That is my adjacent side. Square root of 4 minus 2x plus 1 quantity squared. Now I just answer the tangent problem. Tangent problem, remember, is opposite over adjacent. So I do the opposite side, which is 2x plus 1, over the adjacent side, which is big square root, 4 minus 2x plus 1 squared. This is my answer. The book's answer would FOIL that out, so it'll look a little bit different. Let me show what that looks like. The book's answer should be 2x plus 1 over some variation on 2 minus 4x squared minus 4x. If I had to guess. No. 3. There we go. And these might be a little out of order, but they should be those 3 pieces. Andrew?
Alright, so why isn't sine being an inverse changing anything? I wouldn't like
Well, it did.
Sine
Remember, sine inverse helps us declare what these two components are. We define these two components using the sine function. This one's the this one's the opposite. That one's the hypotenuse. So we use sine inverse to set up this picture.
Right.
But the question asks us to apply that to the tangent problem.
What's the difference between it just being like sine? Because it would still be opposite of hypotenuse, right?
Yeah, but we'd have to have that equal to opposite of hypotenuse. Remember, sine, as a reminder, let me do it down here, okay? Sine, normally you plug in the angle, theta, and you get out opposite of hypotenuse. Whereas the inverse works the opposite way. So what we do is sine inverse plugs in O and H, and you get out theta. To put it another way, you're asking a question like, why don't we just use a square root instead of a square? Because they have different uses. Here's 2. I see the confusion though, because they are so similar, right? I wish they'd use a different symbol. But at the same time, if you use a different symbol, then I'd be saying, hey, learn 3 more symbols today. Haha. So, other questions? That was number 37 and number 41. Any others that stick out from the homework assignment?
43.
43? Sure. Before I go, any questions on 41? All right. Let's do 43. See, all of these are pretty similar. Let's talk about 43.
See you, Doug.
See ya. All right, 43. 43 says, ooh, yes, I love 43. Oh, I was looking at 42. 42 is my favorite question in the homework because it looks so nasty and complicated, but if you look close, it's just even a circle problem. There's like 6 of them. I love it. 43. It says, this will be the only one I actually write the instructions for. If sine of t is equal to x over x plus 1. So as a reminder about this statement, before I look at the problem itself, this means that t in this problem is my angle. Because remember, as we just discussed, thank you, Andrew, what goes into the sine function is the angle. So t is the angle. So I'm going to now draw a picture. It doesn't straight out say draw a picture, but I'm going to just draw what this thing says. It says sine of t is equal to x, which is the opposite, over the hypotenuse, x plus 1. So we have the following system set up. The reason why this is really important is because 43 asks us to do something very specific. It says, what is cosine of t? Well, in this picture, cosine of t would just be adjacent over hypotenuse. So I'm going to approach it just like I did 41. Same way. Same process. So what I do is I find this missing side using Pythagorean's theorem, and then I just write down what cosine of t is. It's a different way of asking the same question. They've given us sine as a ratio. Use it to find cosine. Here we go. I find the missing side. So a squared plus x squared equals x plus 1 squared. Those of you in college algebra, I'm actually going to simplify this down so I actually match the book's answer this time. I think this one's worth doing. Okay, so left-hand side is a squared plus x squared is, of course, just x squared. Right-hand side, boil it out. What is x plus 1 squared? X squared plus 2x plus 1. Beautiful. I subtract the x squared over to get a by itself. So I get a squared equals, if I subtract x squared, the x squareds go away, leaving me with 2x plus 1. And then square root both sides to get a by itself. A is equal to the square root of 2x plus 1. Before I go on, one more time. I used the thing that it told me about in the problem. Sine of t is equal to this, to create this picture involving t and the two sides. The question asked me about cosine. Cosine is adjacent over hypotenuse, which means I need this missing side. I use Pythagorean's theorem to set it up. A squared plus b squared equals c squared. I have now just solved this algebraically, trying to get a by itself. X squared is x squared. As Brian pointed out, x plus 1 squared is x squared plus 2x plus 1 using FOIL. Subtract x squared over, take a square root. I now have the missing side a as the square root of 2x plus 1. I now answer the question. The question says, hey, what's cosine of t? Well, cosine of t is adjacent over hypotenuse. The adjacent is square root of 2x plus 1. The hypotenuse is x plus 1. Here's my solution for 43. If we did not simplify it, it'd look a little different. So this time I chose to simplify it so it matches the book's answer entirely. Again, note how we use one trig function to set up another using an inverse property. Other questions? What do you think, Lisa? Questions? Either from 43 or other problems? Haley, you gave me a weird look.
No, just don't erase it for a minute.
Whoa. No. You got computers and it's gonna take like a month to set up. More computers? You got brand new computers next door. Any other questions for the homework? 47? Okay. Haley, you let me know when you're ready. Oh. I will actually use this picture to do 47. These are all based on the same problem, right?
Yeah.
Sweet.
Okay, you're good.
Okay, ready? 47.
Okay, I mean, you can erase that, but what was the final answer for 41?
For 41, it was,
Square root of 7x something.
I thought it was 2x.
I don't know. I looked up and you were erasing it.
41?
Yeah.
It should have been square root of 2x plus 1 on the bottom. Okay, ready? 47. The answer is T. Yeah, go ahead. Ready? How do I know that? Well, what's the problem asked me? It says, hey, what is tangent inverse of, and what does it say in there? Daisy, would be so kind? Well, look at our picture. Those two pieces are in my picture. There's x, which is on the opposite side to t. There's 2x plus 1, which is on the adjacent side to t. The question is, hey, what value has this as its tangent function? T did. It's the only angle in this picture that has the z, or x is the opposite and square root of 2x plus 1 as the adjacent. Whereas if it had this flipped over, we'd be having a very different conversation. Because then this side would become the opposite side. Because remember, tangent has a defined opposite adjacent hypotenuse. The picture is only in reference to the angle. So let me put this a different way. The only reason x is opposite is because we're focusing on t. With the inverse, you have to work backwards. We have to assume this one is always opposite because it's on top of the tangent function, which means this picture could not be accurate anymore. You have to pay very close attention when dealing with these inverses because this inverse defines reality. That does not mean it's referencing the same picture. It could be talking about a completely different picture. It just happened to be in this case. The correct solution here, t. It is the only angle with the relationship of opposite of x adjacent square root of 2x plus 1. Thank you for that question. Was a good question. It seems so simple for 47 that the answer is just t. Remember, the inverse is always supposed to tell you an angle. The inverse always tells you an angle. So what angle has this property? T does. Other questions? Fix this disaster zone here. That was 47. Other questions? Alright, guess I'll just chill for this. Does anybody have any more?